Geometry Lesson 2.4. We've been studying inductive reasoning. Now we'll move on to deductive reasoning. Deductive reasoning uses given general principles to reach specific conclusions. Those conclusions must be true. Inductive reasoning uses special examples and patterns from special examples to draw general conclusions. So deductive reasoning, we're given general principles and true specific conclusions. Inductive reasoning, we use patterns from special examples and we draw general conclusions. Example 1 says classify each argument as inductive or deductive. All squares are rectangles, and all rectangles are polygons. Therefore, all squares are polygons. The answer to this is deductive. We used established general principles to reach a specific conclusion. Squares and rectangles both have 4 sides. They both have 90-degree angles. Rectangles and polygons both have straight sides. They're both closed curves. We know that squares are also polygons, so therefore all squares are polygons. We've used established information that we already have to reach our conclusion. Let's try B. A meteorologist studied weather patterns for the last 10 years in his city. Based on the trends, he predicts an average high of 25 degrees Fahrenheit in January. They actually have the word patterns in this argument, and they have the word trends in this argument, which is also assumptions made from patterns. So this is an inductive argument. A pattern is seen in specific examples, and it's used to reach a general conclusion. In a reasoned argument, the supporting statements are called premises, and the statement they support is the conclusion. If the connection between the premises and the conclusion is logically correct, it's a valid argument. True premises and valid reasoning produce a true conclusion. When we have true premises and a true conclusion with valid reasoning, we call those arguments sound arguments. Modus tollens is a method of deductive proof based on the contrapositive rule. It has the following symbolic form. If P, then Q. Not Q, therefore not P. So we'll read our original premise. If it is raining, this is P, then I need an umbrella. This is Q. We're now going to do not Q. I don't need an umbrella. Therefore, not P, it is not raining. This now leads us to our first 2-column proof. When we're doing 2-column proofs, we'll have a column of statements and a column of reasons. These statements are given to us from our book. Therefore, the first reason that we'll have is the given, and this will 99% of the time be your first step in doing a proof. So let's look at this statement. P, if P, then Q. Not Q. Let's go back and look at this. If P, then Q, not Q. So we're actually doing the proof for this premise. Not Q, therefore not P, is our original premise that we negated and reversed, and we used the contrapositive rule to do that. Our conclusion is not P. Once again, back to this original conclusion. You can see it right there. And we used modus ponens to establish the not P. This is a proof that modus tollens applies both the contrapositive rule and a modus ponens argument. When we do proofs, you'll be given a great deal of information, and there are actual patterns that will follow. There are common fallacies of assuming the converse and assuming the inverse result from the misuse of modus ponens and modus tollens. Remember that the inverse and the converse are not logically equivalent to the original condition. Here's some examples. If it rains today, the dam will break. It rained, the dam broke. This is a valid argument. Because it rained, the dam will break. It actually rained and the dam broke. Let's take this same premise and give it a different second premise. If it rains today, the dam will break. It did not rain. The dam did not break. We assumed the inverse in this argument. Consequently, it's invalid. The dam didn't break, but we don't know that that's because it didn't rain. The dam might not have broken because it wasn't full enough to break. Let's do a third one. If it rains today, the dam will break. The dam broke. It rained. We're assuming the converse. This is an invalid argument. The dam might have broken whether it rained or not. And a fourth argument. If it rains today, the dam will break. The dam did not break. It did not rain. This premise and conclusion is based on our original premise, and it is valid because of modus tollens. Let's look at an example from your book. All dogs are mammals. Garfield is not a dog, therefore Garfield is not a mammal. Just because Garfield is not a dog doesn't mean that he's not a mammal. He might be a cat. Let's look at this symbolized. If dogs are mammals, so if D, then M. Not dogs, therefore not mammals. The symbology is correct, but it's a fallacy. We're assuming the inverse. The second part of example 3, another argument. All dogs are mammals. Garfield is a mammal, therefore Garfield is a dog. Well, once again, Garfield could be a cat. Symbology, if dogs, then mammals. They're mammals, therefore they're dogs. Once again, this is a fallacy. We're assuming the converse. Because both arguments show invalid reasoning, they are unsound regardless of the truth of the conclusions. The pattern was followed to draw the conclusions, but the reasoning was invalid, so they are unsound. Our third method of deduction is transitivity. This is also called the law of syllogism. It's a method of deductive proof with the following symbolic form. So, if P, then Q. If Q, then R. Therefore, P. If P, then R. We now have three separate statements, and this is a pattern that might seem familiar. This method is the transitive property of equality, and it states A equals B and B equals C, then A equals C. And we learn this when we're learning about properties of addition. Example 4. We're asked which conclusion can be drawn from the following premises using transitivity. So our correct answer needs to use transitivity, which is if P then Q, if Q then R, therefore if R then P. If a triangle is equilateral, then its angles have equal measure. If the angles of a triangle have equal measure, then none of the angles are right angles. And let's put down our first conclusion. If none of the triangle's angles are right angles, the angle is equilateral. The conclusion: therefore, if R, then P. We want an answer that says if P, then R. So conclusion A is not transitive. A triangle is equilateral. The triangle's angles have equal measure. If a triangle has a right angle, it is not equilateral. If P, then Q. If Q, then R. Therefore, not R. If not R, then not P. Remember, we're looking for an answer that says if P, then R. Conclusion B is not the correct answer. Conclusion C. If a triangle is equilateral, the triangle's angles have equal measure, then if the triangle is equilateral, then none of its angles are right angles. This was our original premise that we read and conclusion, and this one is correct. If P, then Q. If Q, then R. Therefore, if P, then R. And the last option you have, a triangle is equilateral. A triangle's angles have equal measure. If a triangle is not equilateral, then it contains a right angle. So if P, then Q. If Q, then R. Therefore, if not P, then not R. This also isn't transitive, because we found our transitive answer is if P, then R. This one is negated, so this is not our correct conclusion. Here's the last example. All of the animals at the San Diego Zoo are zebras. All zebras eat marshmallows. Therefore, all of the animals at the San Diego Zoo eat marshmallows. I'm sure the tigers would be really thrilled with that. Okay? So, first of all the animals at the zoo are zebras is an invalid statement. All zebras eat marshmallows. I doubt it. Marshmallows do not grow in the wild. Therefore, this conclusion drawn from these two premises is not a valid conclusion. All of the animals at the San Diego Zoo eat marshmallows. Both premises are false, so the argument is not sound. Despite being a valid transitivity argument, the reasoning produces an incorrect conclusion. So if I just gave you a homework problem that says create a valid transitivity argument, this would be fine. This original three statements here would be fine. But if I asked you to produce something that has a true conclusion, this is not a sound argument. When examining arguments, be sure to examine the truth of each premise and the validity of the reasoning. Valid reasoning based on true premises produces a sound argument. So this is what the truth table looks like for transitivity. If it's a true premise, and the reasoning is valid, the argument is sound. If it's a true premise, but the reasoning is invalid, the argument is unsound. If it's a false premise, the reasoning is valid, the argument is still unsound. And if it's a false premise and the reasoning is invalid, the argument is unsound. Go ahead and make an attempt to do your homework. We will be reviewing sections 2.1 through 2.4 in class, and we'll practice more of these.